guys, welcome to my YouTube channel. Myself Sagar Girigoda. I'm studying in Sri Venkateswara College, third semester. Today in this session, I am going to discuss about digital design and computer design, and the topic is Introduction to KMap. KMap means Karnaugh maps, commonly known as KMap, are visual tools used in digital logic design to simplify Boolean expression. They provide a systematic and initiative method for minimizing the numbers and logic gates required to implement a given function, resulting in more efficient and cost-effective designs. Definition of K-map. A K-map is graphical representation of a truth table. It arranges the minterms and maxterms of Boolean function in a grid format, where each cell corresponds to a unique combination of input variable. The arrangement of cells is based on gray code pattern, ensuring that adjacent cells differ by only one variable. This arrangement allows for the essay identification of groups of adjacent cells which represent implants or implicates of function. Mean term. Mean term represents a product term of all input variables where each variable appears either as literal or its complement. They correspond to specific rows in the truth table where the output is true. Max terms. Max terms represent a sum term of all input variables where each variable appears either as literal or its complement. They correspond to specific rows in the truth table where the output is false. Advantages of K-map. K-map offers several advantages over traditional algebraic simplification methods, making them a valuable tool for digital logic designers. First one, simplicity. K-map provide a straightforward and visual approach to simplification, reducing the need for complex algebraic manipulations. Minimization. The help They help minimizing the number of logic gates required to implement a function, resulting in smaller, more efficient circuits. Efficiency. They enable rapid identification of implicants and implicates, leading to efficient minimization of Boolean expressions. Flexibility. They are adaptable to various Boolean functions regardless of their size and complexity. Disadvantages of KMap. While KMap are powerful tools, they also have some limitations. Limited size. KMap becomes increasingly complex and difficult to use for functions which a large number of variables. The size of the map grows exponentially with the number of inputs. Don't care conditions. While KMap can handle don't care conditions, it can be challenging to incorporate them effectively, especially in a large maps. Time complexity. For highly complex functions, the time required to manually simplify using K-maps can considerable, especially for beginners. Simplification of Boolean expression using K-map. K-map process of simplifying Boolean expression using K-maps involved several steps, all focused on identifying and combining groups of adjacent cells representing implicants or implicates. Step 1. Construct the K-map. Create a K-map corresponding to the number of inputs variables. Each cell represents a unique minterm or maxterm, and the arrangement follows a gray code pattern. Step 2. Filling the K-map. Filling in the K-map 1s or 0s based on the truth table of the functions. A 1 indicates a minterm that produces a true output, while the 0 represents minterm that produces a false output. Step 3, identify groups. Identifying groups of adjacent cell containing ones. Groups can be horizontal, vertical or diagonal, and they must have power of 2 number of cells. Step 4, write the sum of products expression. For each group, write the corresponding product term, identifying the common literals among the cells in the group. Combine the product term using OR operators to create the simplified sum of products expression. Visualization of Boolean function using KMap. KMap provide a clear and intuitive visual represents mapping truth tables. KMap directly represents the truth table, visually highlighting the relationships between the input combinations and output values. Identifying patterns. The arrangement of cells and the grouping of adjacent cells in one's reveal pattern in the function, making it easier to understand how the output is determined based on the output. Simplifying complexity. By grouping the adjacent cells, KMap simplify complex Boolean expression into smaller, more manageable forms, enhancing comprehensions and making it easier to implement the function using logic gates. Conclusion. KMap provide a visual tool for simplifying Boolean expressions and minimizing the complexity of logical circuits. They offer a visual and intuitive approach to enhance the misunderstandings and efficiency in the digital logic designs. However, it is essential to consider their limitations, particularly for large scale and complex problems. As technology continues to advance, other methods and software tools are merging to address these challenges and provide even more efficient solutions for digital logic optimization. Thank you for watching. Please like, share, and subscribe.